Welcome to the analysis and design of a flyback converter. This is part 19, Transformer design. Okay, on part 18, I went through the design procedure and I probably jumped around a little bit too much. So what I'm going to do is I'm going to go ahead and review the procedure, and I'm written it down here as in steps. So I'm going to go ahead and review it. Now, I would like to ask some feedback to see whether this material is making sense or not. Am I going too fast or am I going too slow? So any kind of feedback that you can provide to me via email would be great, or you can post it on my channel. Okay, so let's go ahead and let me make this a little bit bigger. Okay, so the first equation, or the first step, is we calculate LM, or actually the primary of the flyback. So video 1, 2, and 3 is basically the analysis and deriving this equation. Okay, the equation that I have here is a little bit different. I'm gonna went ahead and condensed it in terms of P out and so forth. Okay, but you can use this equation as well. Okay, after you have done you have calculated the primary inductance that is required to make your flyback work, then you need to select a core, a transformer core. Okay, so how do you do that? Okay, well, what you want to do is you want to use this equation. Okay, and this equation, I believe it's from one of the TI application notes on transformer design. Okay, so that's where this originally comes from, or at least that's where I've seen it. And basically AP is called the area product. Okay, why? Well, what they do is they get the winding area and the effective area of your core, and they multiply it. And since they're areas, right, so they're squared, typically cm squared. When you multiply, you end up with cm to the fourth. Okay, so this is the equation that you use. Okay, so what is it that what inputs do you need? Okay, well, PO is actually your power output. Okay, and that's from your design. And set that in red. Okay, F sub SW, that's your switching frequency. Okay, so that's also from your design. Okay, K, that's a given. That's basically for a flyback. Or a forward. There are other constants for a bridge and so forth, but for right now, since we're doing a flyback, we're using K as 0.014. Okay, so in reality, the only variable that you have, or that you have a little bit of control and that you choose, is your delta V. Okay, which is your flux. Okay, so I know that I'm going to change the labeling a little bit, and keep in mind when you're using this equation to find the area product, go ahead and use a delta B of 0.16 for right now, and this value comes from the Pressman book. Okay, so to calculate the area, use that as your basis, and you're going to end up with, like I said, the area product. Okay. So once you have the area product, you go to the third step. The third step is you select a core based on your AP results, and you look at a data sheet or a table to find an AP that's large enough. Okay. So in that case, let me go ahead go up back to my table. Okay. And if you notice here, these are my core types. And right here, this is my AP. And whatever AP you calculated, make sure you select a core that is of higher value, because if you select one that is lower, then it's not going to work. You can select something bigger but not lower. Okay, so be sure that you select one that is big enough. Okay, so now in my example, I'm selecting an AP, I'm sorry, a EFD20, and I need 3 pieces of information. Let me go ahead, go back and see what are the information that you need. Okay, so we've already completed here. We select the core, and I selected a EFD, I believe, 20. Okay, and I need to select number 4. It says once core is selected based on AP, find 3 parameters. Okay, what are the 3 parameters? Here they are. This is the first one, AE, the effective cross-sectional area, VE, the effective volume, and I labeled this as W sub W, which is the winding width. And if you notice, these are the units. Okay, so let's go back up to the table. Okay, and if you notice, here's my AE. Okay, here's my winding width, and here's my volume, effective volume. Okay, and of course the units are right there, right there, and right there. Okay, so you need those 3 parameters once you have selected your core. Okay, so we're down here. Okay, so now the first parameter that we're going to be using is your AE. Okay, once you do your AE, then you use that to do what? Actually, what we do is we use that to find the number of turns that will make your transformer work and not saturate. Okay, let me explain that a little bit. Let me go over this equation. Okay, this equation says that it's the n turns, basically the number of turns that your primary will have. Okay, and these two are equivalent. You can use either one. Okay, again, Vn is your input, that's your parameter, that's your design. You designed for the duty cycle. That's comes the F sub W SW. That's your design, and you've already selected your core. And since you selected your core, you should have that value. So you enter it here. Okay. Now the only variable that you now have, and I labeled this a little bit different. Okay. I labeled it as delta B operate. Okay. So it's a little bit different from the first one. Okay. On the other one, I set this to the delta B to 0.16. Okay. On this one, we have a little bit more leeway. Okay. So this is the flux that the transformer will be operating. Okay. Now take a look at this. Let's look at the equation. Okay. If you notice, the only variable that you're going to be varying is your delta B operate. Okay. Everything is pretty much fixed unless you select a different core. Okay. But if you look, your delta B operate is in the denominator. Okay. And if you increase your delta B operate, what happens to end turns? The number of turns actually goes down, which is good. Which is what you really want. Okay. You want this. You don't want a lot of windings. Okay. You want as few as windings as possible. However, then you might say, well, let's start cranking this all the way up and make this as low as possible. Well, can't do that. Okay. There's a limit. You can only operate this at a certain level. Why? Well, because the transformers have what is called a BSAT value. That's the value where it saturates. And that's bad. You do not want a transformer that saturates. What happens? When it saturates, the current actually goes high. It goes up and it destroys your MOSFET. It kills it. It zaps it. As a matter of fact, when you saturate the core, if you look at the primary from the previous videos, you know that the primary current is supposed to look something like this. A sawtooth. Okay? But when you saturate the core, and remember, that's the peak current, that value right there. But when you don't design it correctly, and you use a value that is too high, then when the current goes up, it'll do this. It goes way up. Okay, so if you see a waveform, a current waveform, and it looks like this, where instead of having a linear and it spikes up like this, your transformer's saturating. Okay, so you don't want that. Okay, very important. Okay, so then how do you set this? Okay, so I'm going to give you some guidelines or rule. Okay, let me, instead of a rule, let me just a guideline. Okay. Okay. You want to vary or keep your delta B operate. It has to be, well, you know what? That is correct. What I had before. It's a rule. this was the rule. Basically what I'm saying is this part, that your B delta B operate should be less than your B saturate. That's a rule. Never violate that. You never want this higher than this. Okay? So in my example, I'm using, I believe, a 3F3 core. The BSAT is 0.37 Teslas at 100 degrees C. So I'm never supposed to exceed this. Okay? So here's the guideline. Okay? So the guideline is, go ahead and start with a minimum of 0.16 Tesla. And remember, this comes from the Pressman book. Okay? And you can go up to 80% of BSAT. Okay? So as long as you stay within that range, to that range, you should be fine. Okay? And let me okay, so let's assume 370 times 0.8. So in this case, I can go up to 0. What was it? 296. 296 Tesla. Okay. So from 0.16 Teslas to 0.296 Teslas. So what does that give you? Well, it gives you 20% margin. Okay. So you have enough margin that hopefully you won't saturate. Okay. So this is the guideline that I suggest you follow for that. Okay. Okay. So now I just want to make another side note. Okay, which is very important. Okay. As I had mentioned before, and look at the equation, as your delta B operate goes up, I made a statement that the end turns goes down, which is good. Okay. But on the other hand, what it does, your core losses, in other words, power losses in the core, actually goes up. Okay. So let's see why I'm making that statement. Okay. Well, then we'll go step number 6, and we'll use, I believe, the second, or VE. Yes, VE. That's the second parameter. VE, very important. Okay. So once you have VE, you can find the core losses. Okay. And to be able to calculate the core losses, you have to know what the material that you're using. In this case, I'm using a 3F3. Okay. And in your magnetic books, they always have a plot that looks like this, which is your power loss. Okay, it's your PV sub B. And if you notice, it's expressed as kilowatts per meter cubed. Okay, so this is a power loss. It's a kind of like a power density. Okay, and if you notice, excuse me, if you notice your x-axis, the units are milliteslas. Okay, which means that this is 10 millitesla. That would be 100, which is really 0.1 Tesla. Okay. And I believe in the example that I used in the last, I think I used something close to 0.2 in the example. Or let's just assume that I'm going to use a delta operate of 0.2 Tesla. Okay. Well, in this case, 0.2 is right here because this is 0.1 Tesla. This is 0.2 Teslas. Okay. And if you look in here, you notice that there's this plot that corresponds when your frequency, switching frequency, is 25 kilohertz, 100, 200, 400, and 700. So in the design example, I'm using 100 kilohertz. So you come up here. Okay, you notice intersects right there. And this is 10, 100, 100, 2, 3, 4. So it's about 450 going across. So it's 450 kilowatts per meter cubed. So you get that value. This is your PV value based on a Tesla of 0.2 Tesla. Remember, this is the flux that you're operating your transformer. Okay. Now, keep in mind, if you operate at a higher level, let's say at 0.3 Tesla, if you go up here, you'll notice that you'll have to extrapolate that. Looks like it comes up here, and you end up with, this is 1,000, 2,000, so it's about 1,500 kilowatt per meter cube. So basically, you have higher power losses as you increase this much. With only a 0.1 Tesla increase, you got quite a bit of power loss. Okay, so let's go ahead and calculate how much power we're going to be losing or wasting. Okay, again, this is the core. This is the material that I'm using. That's where we got the little chart up above. And we calculated a PV from the chart of 450 kilowatts meter cubed. And this comes from our second parameter. Okay. And to calculate the core losses, you multiply PV times VE. Okay. So in this case, what I went and did is I converted the 1.46 centimeters cube into meters cube. Here's VE. This is VE right here. And this is PV. So I end up with a core loss due to the magnetic material of a little bit over a half a watt, basically 657 milliwatts. Okay, so you're not even considering power losses in the wire yet. This is losses in the core. The core actually heats up. Okay, so we're up to there. Okay, so now we're going to use the third parameter, which is this W sub W. This is the third parameter from the data sheet. Okay, and we're going to try and determine since we already have the end turns already calculated, we're going to do like a first try on trying to select. Basically, this is really, you want to select a wire. Okay, so how do you do that? How do you select? Okay, well, if we know what this is, a cross-sectional side of the the bobbin, and if we know the length or the width rather, okay, and if we know when we already calculate what the end turns are, then we typically try to fill that in one layer. Okay, so if you know how many turns, and remember the windings look something like this. Okay, so basically you have a conductor, conductor, conductor. You're filling up these spaces. Okay, so the number that you can fill up and the number that you already know, then you know that you can calculate what the diameter of the wire is. Okay, so that's what this equation is. Basically, your W sub W divided by the end turns will give you a rough estimate of the diameter of the wire. Okay, so in the design example, V sub W is 1.35 centimeters, and we had calculated in the previous example that I needed 17 turns. So I need a conductor, a wire, that's approximately 0.794 millimeters. Okay, so you can look in a wire table, and in my case, a 12 gauge of 20 was rather close. It's a little bit bigger, but I went ahead and selected it. But that's the conductor, and it would be the first pass. Okay. And the reason I say this, because this is iterative. In other words, you try a first pass, and if it doesn't meet all your other specs, then you can change that. Okay. So then, once we selected the gauge, we want to make sure, or actually we want to verify, that the selected wire gauge can carry the current. Okay, so you should have this equation from the Flyback analysis. It's the I primary RMS. Okay, that's the equation for that. Okay, and you want to be sure that the current, that the wire, or the wire that you selected, is greater than this I primary RMS. Okay, so you want this bigger. Okay, so you always check that. Okay, and how do you know what is the current carrying capability of the wire? Well, you can look it up in a table. You can search it on Google, and there's a lot of tables where you can find you can look at the gauge, and you can calculate, and well, it tells you the current. If you don't have a table, then you can use this equation. That would also give you an approximate, as long as you know what the diameter is. Okay, so if you plug the diameter in here, you can calculate the fusing current, and this should match very close to your table. Okay. Okay, so basically up to now it's still been a review, and hopefully it made sense. So this is the new material. Okay, and I'm going to cover skin effects and the proximity losses and try to explain a little bit what they are and how they affect the circuit. Okay, so let's start with this skin effect. Well, basically, as your frequency goes up, the electrons flow on the outer skin of the wire. Okay, so basically, if you have a conductor, and let's say this is the cross sectional, and let's say you're operating at DC. DC means that the frequency is 0. And if you were to take a cross section, and if you could look at the atoms or the electrons, you would see that they're equally spaced throughout the conductor. Okay, but since we're operating at a frequency of 100 kilohertz, that is no longer the case. Okay, as the frequency goes up, then the electrons, they start bunching up on the outer skin. Okay, it's not working as well, but anyway, so you end up with a center where you don't have basically no current or no electrons actually flowing. Most of the current is flowing through this band. Okay, so what does that do? What's the big deal? Well, the effect is that since you have less of an area, it increases the resistance of the wire. So basically, as your frequency goes up, the resistance of the wire goes up as well. Okay. Proximity. Okay. What's that? Well, this is having to do with eddy currents. Okay. And if you have, let's say, one conductor here, and then you have another conductor here. Okay. And let's say I'm going to put a dot in here, meaning that current is flowing into. Okay. And if current is going into, then it develops a, let me see, a magnetic field that goes using the right hand rule. Let's see, it's going in, the thumb goes in, so my hand goes in this direction, so that means the magnetic field goes in this direction. Okay, and it's in another conductor. Okay, well, since that field is cutting into the conductor, then what it does, it starts conducting current around the inductor, and that current is called eddy current. Okay, heats up your conductor. Okay, and the more conductors you have stacked up, the greater the field and the more losses you have. Okay, so basically, as you increase the layer, the power losses goes up, and your AC resistance also goes up. So all of these are bad effects. those are effects that you do not want. Okay? And when I say number of layers, remember, the main goal when you're winding your transformers, you want to wind them in one layer. But you may have a situation where you have a lot of turns and you can't fit them in one layer, so you might have to go use up one layer, a second layer, and a third layer. Now once you start doing this and they start stacking up like this, then that's when you start having a lot of proximity effects losses. So as the layers go up, which is what I'm trying to explain, as the number of layers start building up, your power losses are going to go up, and the AC resistance will also go up. Okay? And that can be explained from what is called the Dowell equation and plots. Okay? So this is the Dowell equation. Okay? You can put this in a MathCAD or an Excel, or you can look up your Dowell plots. Okay. Now I have a very unique Dowell plot. It's very unique. I haven't seen another one quite like this, but this is a great plot. It's very intuitive. Okay. Let me go ahead and explain this. But this is a really, really neat Dowell plot. And you can use this to calculate power losses. Okay. So let's take a look at the y-axis. Okay. If you notice, here's the y-axis. And it says FR is equal to RAC plus RDC. So what does that mean? Okay. Well, if you solve for RAC, you'll see that it's FR. FR is actually a constant. Okay. So let's assume that you have a DC resistance. The wire has a DC resistance of 1 ohm, just to make it easy. Okay. And let's say you end up with a plot, and you look up and you have a FR of 20. Well, now your AC resistance is 20 times 1 ohms equals 20 ohms. So now your resistance has increased by a factor of 20. That's a lot. Okay? So this is what the y-axis tells you. Okay? Now this is typical. All of the other Dowell plots that I've seen show this. What's different is that the other ones that I've seen, they plot this as the diameter versus the penetration or the skin effect. But this is unique in that they have the x-axis in terms of AWG. In other words, they're expressing this as wire gauge, American wire gauge, which is great, because then I can take a look here and I can say, oh, if I use a 12 gauge wire, then I know that all I have to do is go up and I can get my information. Or if I use a 26 gauge, then I go up and I get my information. So this is very unique. So that's why I love this plot, because I can do calculations extremely fast. Okay, so let's give you an example. Okay, and we'll do an example, but let me go ahead and talk a little bit about the bobbing because they're interrelated. Very important. Okay. Number 10. These are kind of like guidelines. Again, winding your bobbin. Okay. Your bobbin is typically going to look something like that. And one of the statement was that as the number of layers goes up, that your power losses goes up. So what we're trying to do is we're trying to minimize this. We want to make this as small as possible. So what are you trying to do? To minimize the proximity losses, we try to wind the primary and or any other windings and use one layer if possible. Okay? So basically you want, if you can, one layer. If you use one layer, that will minimize your proximity losses. Okay? But in some cases, you may have so many layers or turns, you can't wind them in one layer. You may have to use 1, 2, 3 layers. Okay? So what can you do? Okay? And what would be the effect if you were to use 3 layers? Okay? So this is the example that I'm going to be using. Okay? In this case, let's use the example that I used and use a American wire gauge of 20. Okay? And let's assume that I have a DC resistance of 100 milliohms. Okay. So let's use the Dow plot to figure out the power losses. Okay. Based on a transformer being built with 3 layers. Okay. So this is where the power of this comes in. Okay. So the first layer, let's calculate the power loss of the first layer. Okay. So remember, each has 100 milliohms, 100 milliohms, 100 milliohms. Okay. So we're going to calculate the first one. Okay. And since we're using a 20 gauge, here's 20 approximately, and we'll go ahead and go up to close enough. Okay. So if you notice, I'm going to go green. This plot is the plot for the 1 layer, 1L. So then, if you go horizontally, and I'll say that that's 3. Okay. So I have an FR of 3. Okay. So the first layer. So the AC resistance is equal to FR times the DC resistance. So I calculated from the Dow that it has a factor FR of 3 times 100 milliohms. You get 300 milliohms. Okay. So it increased by a factor of 3. So now let's calculate the resistance of the second layer. Here's the second layer. Okay. So you come up here again, and now we're going to look at layer number 2. Notice this is layer number 3, no 2. Okay. So now we go sideways. And I get, it's either 12 or 13 would be my guess. Let's see what let's see. Oh, sorry. I went to the layer number 3. Here's layer number 2. That's 7. So this is 3 FR. That's 7. This is the first layer. Second layer. Third layer. So the second is 7. So now the AC resistance on the second is 7 times 100. So now you have 700 milliohms. And then the third, where we already found, we found that it's either 12 or 13. Okay. I went ahead and used 13. So now the resistance is 1300 milliohms. So now, since they're connected in series, you end up with a resistance of approximately 2.3 ohms. Okay? So this is for 3 layers. So if you were able to fit it in 1 layer, you would only have had 300 milliohms. Instead, you end up with 2.3 ohms, which is a lot. Okay. So here's another guideline. What do you do to try to minimize it? We already said that you try to minimize it by using as the least amount of layers as possible. But the other thing that you can do is you can use a smaller wire to minimize the losses. Well, how do we determine that? Okay, well, let's look at the plots. Okay, if you notice, these, as you go up, the diameter are bigger in that direction. So if you go in this direction, select a AW that is large, which means really that it's smaller, it's a smaller diameter, then you're operating in this level. So let's say if I was to use a 30 gauge, and the first layer is basically a little bit above 1, and if you go to 2, 2 is right there. 2 is above 1 but below 2, and the third layer would be right here, and it would be still be above 1 but still below 2. So the FR that you would get using a smaller diameter is much lower. So your losses are going to be lower. Okay, so that's why I like using this plot, because it gives you a intuitive feel of your wire and how it affects your losses. Okay, and I'm going to go ahead and stop here. I hope this has made sense. It's a lot of information, but if you do have questions, please email me with your questions at my email address, or you can post them on my YouTube channel. Like I said, If you can give me also some feedback whether the tempo is correct or not, or if I'm too slow, and so forth. Thank you for watching.